The objective of Constellation is to return humans to get humans beyond low Earth orbit, to build new vehicles, new launch vehicle, new human carrying vehicles, first up to space station, and then as soon as we can onto the moon. And from there, we're looking at Mars. So the system is overall looking toward expanding human presence through exploration, outside low Earth orbit. I think it really started with an ESAS study, which was almost 3 years ago now. And that study was really looking to solve that problem. How do we now return humans to the moon and beyond, but to do that for a long duration, to go from a 3-day Apollo stay to a week to 2 weeks to 6 months. And ultimately, if we're going to go to Mars, it's going to be a 3-year mission. ESAS pretty much covered the entire range of elements that would be needed to take humans beyond low Earth orbit. So new vehicles, new crew-carrying vehicles, new launch vehicles. It fundamentally created an architecture that was really required 2 launches in order to get enough mass and material up into low Earth orbit to go to the moon. Apollo, of course, did it with 1 on the Saturn V. But we now have 2 vehicles, one of which is called Ares V, which is 50% more capable than even Saturn V was. But we can't launch the crew and our lunar landers on one vehicle. We're still trying to deliver that much more mass to the surface of the moon. And with the gear ratios we have, we really need we need 2 launches with a rendezvous in low Earth orbit. Well, I think overall the architecture was pretty sound. We pushed on it, we tested it, we didn't find any fundamental flaws in the overall concept, but what we did find is there was inadequate margin. Well, margins are, the coin of the realm for systems engineers. And in this case, I was really brought in originally to understand what the mass and performance picture was for Ares and Orion. And was it broken? And if so, how badly was it broken? And there were a number of problems with Orion. The mass had been growing, and this is again where we ended up having to, dropping back to a 1 failure tolerant system. That helped take a lot of mass out for redundancy. But it still left us, with an uncertainty as to whether we would have enough margin when we were pre-PDR to get through to the launch pad. And Apollo certainly had a lot of mass problems. We learned a lot from looking at Apollo. So I came in from my own experience saying I want to see a certain margin at PDR. In fact, I want a certain margin pre-PDR. And that ought to be in the order of 30%. Well, we were nowhere near 30% margin at that point. And that was just on Ares and Orion. Now, when I looked at Altair and Ares V, again, the same sort of thing. How do we, I wanted to see enough margin to protect us for the uncertainties that were ahead of us and to protect for the unknown unknowns. ESAS was really a clean sheet of paper, and both Ares 1 and Orion were proceeding along. We were getting a better understanding of what those vehicles looked like, what their performance was, how much they were weighing, what they could carry in terms of payload. And at the same time, we kicked off the Altair lunar lander and the Ares V teams. So we had all 4 project elements moving along in parallel. In addition, we had a lunar surface systems project, which was trying to figure out what systems do we want to land on the moon? What capabilities do we want to have for mobility, for habitation? And so you took all 5 of those, and we needed to knit those together. And that was really my office's job, with a great team of people from around the agency. And we took all those pieces and worked with each of the projects to adjust what we needed from them, what performance we needed to get, what payload they could carry, et cetera, et cetera. This last June, at a Lunar Capability Concept Review, we presented to the administrator an end-to-end architecture that closed. It closed on performance, it closed on overall capability, had the kind of future capabilities we were looking for. So we closed on mass, we closed on performance. We were close enough on dollars. It's still pretty early on dollars. Looked okay from a risk point of view, but all those things are things we still need to continue to work on. But overall, the architecture was satisfactorily closed. The range of risks that we need to consider when we're doing these kind of systems. The first, were the technical risks, and those are pretty well, understood. Performance of we're building new vehicles, new engines. One of the things that we had to we recognized early on when you talk about leaving Earth orbit, you've got some big gear ratios involved. So the previous strategy in human space flight was, make everything just two fault tolerant. Make it fully block redundant. And we couldn't afford that. We couldn't afford the mass to do that. So we dropped back to a one failure tolerant design. And that's for Orion, that's for Ares. It's going to be for Ares 5. It's going to be for Altair. So how do we make that sort of a system as reliable as it needs to be to carry humans, and to do it not just for a short mission, but for days, weeks, months? So that's an inherent risk that is going to be a challenge for us throughout the life of Constellation. But it's something I'm used to in the robotic world. All of our systems are at best one failure tolerant, and oftentimes they're zero failure tolerant. And you look at the Mars rovers, Spirit and Opportunity, just celebrated 5 years on the surface of Mars. Those are both zero fault tolerant machines. So we know how to build high reliability stuff, but it's convincing ourselves and convincing the public and our sponsors that we have a good design that's really important. So technical risks. The other risks are programmatic. How do we do this within the fixed budget that we have? And that continues to be a challenge. There's a lot to do. It may seem like a lot of money, but when you have so many different systems that have to come together and work together effectively, it's a lot of resources you need to apply. And I think we've tapped very effectively into the NASA family. We're really using all the NASA centers to help us, as well as a great great contractor teams throughout the country. So I picked numbers that I felt were challenging and would be give us some reasonable confidence of being successful. Though they really pushed us, particularly pushed us for performance in the Ares 5. So I again used historical precedent and experience and whatnot to kind of pick those numbers, but I knew that those numbers couldn't stand on their own. And when you talk about a multi-stage system like this, you can't just apply 20 or 30% margin to every segment. Pretty soon, because one segment is boosting another, so you're putting margin on top of margin. So I'd seen that from my work on Mars sample return and other multi-stage complex systems. So just speccing a number wasn't going to be enough. So what I did as part of the architecture work was draw on some experts in stochastic analysis, and we built up some models, historically based, that gave us a basis for defining probability density functions that would allow us to combine in a way to estimate the amount of margin we would need, and then we could pick how confident, pick my confidence number. Do I want to be 90% confident I have enough margin? Do I want to be 95%? Do I want to be 99%? Same sort of stuff we do actually with budgets these days, So it was a significant amount of work to first build the historical database. And we were able to, again, go back to Apollo. We really had to dig to find, the time history of mass for missions like Apollo, for Skylab, for Shuttle. But we were able to put that together, and then we combined that with our models of Altair and Ares 5, Orion, Ares 1, and we're able to derive a overall probability density function of having enough margin to accomplish the program. There were really two major elements we had to trade against. One was the mass of the vehicles that we had to inject to the moon, which was Orion and Altair, against the performance of the launch vehicle, Ares 5. And so within both of those, there were certain potentially big drivers for performance, or for either mass or performance. On the performance side, for Ares 5, clearly the performance of the engines, the J2X, on the Earth departure stage was a key performance. Other was the performance of the R68 engines. Most of the other elements were pretty well characterized. We thought we understood, the solid rocket boosters. On the Orion side and the Altair side, again, it was particularly on the Altair side, it was again the performance of the engines. Altair has to do the braking maneuver at the moon as well as the descent and the ascent. So it's got three key propulsive maneuvers that it has to accomplish. So working again with the project teams, we looked at those, and we characterized the probability density function around those uncertainties. We played with ISP, we played with thrust, etc. So it gave us some confidence around the numbers. And then we tapped into a contractor in the Houston area who derived a complete probability model for the Ares 5. And we worked with them to understand all the different parameters that go in, weight of the structure, etc. So we were able to, through multiple paths, derive more and more confidence in the probability density functions we were using. A key thing in doing anything with stochastic analysis is the confidence that you have in the data going in, because that completely drives what comes out. And again, it went to the size of the margin. If your confidence is high, if your models are mature, if your design is mature, then you don't need as much margin. But if your confidence is low, you better have more margin. So what I needed to communicate and get management to accept, and they did, was, I can draw a probability, cumulative distribution function. I can pick a point on that says that's enough margin. But today, given our relatively low confidence, I want a high probability of having enough margin. So I want a 99%. I'm not going to accept an 80% or something like that. Now, at some point in the future, after CDR for Ares 1 and Orion, then we should be able to pick a lower confidence number and feel good that we've got enough margin. So there's judgment. You can't just apply a formula to it. And so you've got to use your judgment about what's enough and work with the management because it costs money. Margin costs money. And you don't want to have extra margin sitting on the launch pad because you probably wasted money preserving it. So it's an art to balance manage our margins. When we set up the architecture team, we first of all structured the team to cover the full range of issues we expected to have to deal with, which were technical, they were programmatic, they were risk. And then starting with the basic architecture from the basic elements of the architecture, we worked with each of the projects to define what we kind of targets for what we expected them to be able to do. We set a mass number for the lunar lander. We set a performance number for Altair or for Ares 5. We already had pretty good sense of what we needed from Orion. Again, a critical element in the overall string. And then we proceeded through an iterative process, looking at, as the designs matured, were we holding the original estimates for margin? Meanwhile, in parallel, we started this stochastic work. So as the designs matured and as we worked toward our review in June, it actually came together very nicely. We'd had all the right pieces were there. I think a key part of any activity like this was the quality of the team and how tightly knit together they were. It was we weren't co-located. I would have loved to get everybody in one facility, but we were spread around the country. But we interacted regularly. We had numerous face-to-face meetings, and that allowed us to be very quick and responsive when problems showed up. For example, we were worried about a performance, say on Altair. Maybe the mass was looking a little high. So what can we do to improve that? What options do we have? Can we do something on the architecture side? Can we do something on the project side? So there was a lot of give and take, a lot of interaction between the various elements. But in the last, as we worked toward the closing the architecture, the key was the stochastic analysis coming together and the recognition that of how we would fly the missions. The first thing we needed to do was set criteria, and establish our figures of merit, and then set some criteria for success. Then we worked with communicated that to each of the projects, and worked with the projects for them to meet their criteria. Whether the criteria was mass, it was performance, it might be a risk number, a Loch-Lomb number. And then we started in the iteration process against the figures of merit, looking to see that the architecture was achieving its mission objectives. Could we achieve the duration of the missions on the surface of the moon? Could we get to where we wanted to go? Our primary initial objective is one of the poles, and the South Pole is the nominal target, and that's where we'd like to set a base up. But in addition, we wanted to cover almost everywhere on the surface of the moon. So we looked from a mission design point of view and from an overall performance point of view. So after, again, clear understanding of what our objectives were, where our targets were, our margins, and then we continued through the iteration process. We saw breaks, we saw problems, we moved to fix those, and in the end, we brought in the stochastic analysis, which allowed us to show probabilistically that in fact we could close on performance. So we use stochastic analysis for cost as well. So we provide, and of course it's a big part of any risk analysis. So stochastic analysis is really the bread and butter, I think, of architecting today. So all of that we needed then to bring together and package in a way where we could communicate it to program and NASA leadership, that we'd established the rules, we'd played the game, we'd succeeded in meeting the criteria that we'd established. So at the concept review back in June, unanimous agreement from senior leadership, including the administrator, that we'd accomplished what we'd set out to do. We had a closed architecture for the transportation system for returning humans to the moon. It wasn't the architecture, it was an architecture that would work, and then we had time to continue to iterate that, improve it, add more capabilities, etc. Well, the first and most important is always, it's the quality of the people, putting together a great team and leading that team well, having a clear understanding of where you're going, and the leadership being effective in helping focus it, keeping the team focused and facilitating them getting to their goal. The second part is the second key lesson learned is thinking stochastically, thinking probabilistically, thinking about the nature of the uncertainties in these very complex systems. They do not lend themselves to deterministic or kind of worst case analysis. So the use of stochastic methods for thinking about complex problems is really fundamental, I think, now to the way people need to solve many engineering problems and certainly architecture problems. And finally, for an effective architecture, you need to have robust margins. Whether the margin, when you're doing architecting, you're up front, you're early in the development phase, and you need to maintain this architecture throughout its life cycle. So it needs to start with robust margins, mass, performance, power, all those technical degrees of freedom. Also need cost. You need programmatic margins. You need cost margin. You need schedule margin. All those three elements together are really the degrees of freedom you need to define and maintain an architecture over a long program like Constellation.